This video is the first in a series where we talk about generalities of acids and bases. Right, so we start by defining what an acid and a base is. The first person to realize the differences between acids and bases was Arrhenius. And what Arrhenius thought is that an acid is something that produces protons when put in solution, and a base is something that produces hydroxide ions when put in solution. However, that definition was later redefined or improved by Bronsted and Lowry. And the definition that we use for acid-base equilibria today is one where an acid is a substance that generates a proton when put in solution, and then a base will be a substance that accepts a proton when put in solution. All right, so we've already talked a little bit about acids and bases the last semester, and remember that for acids we made a distinction between weak acids and strong acids. Okay, so typical strong acids that we remember from our early work were hydrochloric acid, hydrobromic acid, hydroiodic acid, then we also have nitric acid, and then chloric, perchloric. These are all strong acids, and then we also have sulfuric acid. And weak acids would be things like acetic acid and so forth. Okay, so what we can actually do is take these acids and then notice that they all have something that is common, and that is the presence of at least one proton, and then an ion here that is connected to that proton. Okay, and the exception will be sulfuric acid that has two protons, but aside from sulfuric acid, then the rest can be categorized as simply HA, where H is the proton. So then from this definition we can look at the equilibrium that provides acidity, right? So the idea is that when you put this in water, because these are acids, you will generate a proton, that is the definition, and then A minus, which is what we call a conjugate base. Okay? Now there's another way to write this equilibrium that people, that is quite common in the literature, and that is to include explicitly water as a liquid, just to show that this happens in aqueous solution. And these are reversible equilibria, okay, but you get it essentially the same. It's H3O plus in aqueous solution plus that conjugate base. Okay. Now, so which one is more correct? Well, both of them are correct. It turns out that in general, when you have a proton in solution, it rarely is going to be by itself. We know of a variety of structures in which water molecules are connected directly through that proton, and you have these sort of hydrogen ions and higher ordered ions that seem to appear in solution. So this might be a better representation of reality, but for all purposes of any intent of our discussion, this is equally good. Okay, so we're probably going to be using that more often than not. Okay, so the differences between strong acid and weak acids are very simple by just looking at this diagram, right? So a strong acid will have the equilibrium very displaced to the right. Okay, that means that if you put a little bit of HCl in solution, then there will be almost none of this form of the acid left. Most of it will be forming part of protons and then chloride. Okay, so that will be your weak acid, so your strong acid. A weak acid will be exactly the opposite. In a weak acid, what you will have is that the equilibrium will be displaced mostly to the left, okay, so that there are very few protons in solution. You have mostly an dissociated acid. Okay, so that is one of the first distinctions between weak and strong acids that we can do by simply looking at the equilibrium. We can also write the equilibrium constant for both of those processes. So the top one will be like this: H plus, A minus, and then in the denominator you will have HA. This is the short form where we're no longer writing the reference states. Or if you choose this equilibrium to represent what's really happening in reality, you will have this hydrogen ion, which is a placeholder for a proton, or has the same behavior as a proton, and then HA as well. That is that water does not appear in this expression because that's a liquid, and it's the only liquid that you have in the reaction medium, so the activity will be 1. Okay, this type of equilibrium constants, because it's an acid dissociation, we generally call them K sub A. Okay, so that is what K sub A means. What K sub A is the equilibrium constant of a dissociation equilibrium for an acid. Okay, so going back to trying to separate weak acids and strong acids, what we can do then is try to estimate what a reasonable value of Ka would be for a strong acid and what a reasonable value would be for a weak acid. Okay, so if you have a strong acid, what will happen is that this K sub A is going to be larger than 1. Okay, so we know that the equilibrium will be displaced to the right, so most of what you have at equilibrium will be a proton and then the conjugate base, which is these two, and then very little left. What that means is that the numerator is very high, the denominator is very low, and then that is going to give you a K sub A that is larger than 1. If the acid is weak, then what will happen is that this K sub A is going to be less than 1, so you will have mostly unreacted acid at equilibrium, and often it's going to happen that this K sub A is going to be much lower than 1. Okay, so for example, we have seen an example of acetic acid in prior videos in which the K sub A for this process, this acetic acid in solution, and then this dissociates into protons and acetate. The K sub A value for this particular weak acid was 1.8, 10 to the minus 5, which clearly tells you that that's a number much lower than 1, and again, that's a weak acid. That is exactly the hallmark of weak acid. But if this is a very small value, that means that you have a very small numerator, a large denominator, and ultimately what this means is that the equilibrium is displaced to the left. There's very little acid that dissociates to generate those protons. Okay, so again, we're trying to define here generalities of acids, and then we're trying to see metrics that are able to tell apart acids, weak acids and strong acids. There's one more way that you can distinguish or talk about the differences between a strong acid and a weak acid, and that is by looking at the conjugate base. Okay, so I'm going to take this equilibrium that we have written right here and then write it as an acid-base equilibrium. Notice that this is an acid because it provides protons, okay, which are right here, and this is a base because it accepts the proton of that acid, right? So that water in this reaction is actually acting as a base, okay? And then to the other side, what happens is that we have the conjugate pairs of these acids and base, right? So notice that this hydronium can be an acid because it can dissociate into H plus and H2O, right? So that would be the conjugate acid of this base, okay? And likewise, this now can accept a proton to generate HA, so this is what we call the conjugate base of this acid. Okay, so notice how you always have these conjugate pairs, acids and bases, in acid-base equilibrium, right? So a way to tell apart between strong acids and weak acids, or to tell the difference between them, is to compare the strengths of the bases that are involved. Okay, so in this particular equilibrium, what happens is that if we compare the strength of that base to the strength of that base, we can determine whether you have a weak acid or a strong acid. Okay? In a strong acid, what will happen is that the equilibrium is displaced to the right, so that means that this base is very weak, right? The back reaction is actually not very important. Mostly the reaction is displaced that way. That happens for a strong acid. And what that means is that this base is actually a much better base than that one, right? This base does not have a lot of affinity for the proton, so the equilibrium does not move to the left at all. Instead, this base has more affinity for that proton, and the equilibrium is displaced to the right. That's what will happen for a strong acid. Conversely, for a weak acid, you will have that the conjugate base is actually stronger than the base that is eliciting the reaction, right? For a weak acid, what we'll have is that mostly the equilibrium is displaced to the right. That means that this conjugate base has a really high affinity for that proton, or an affinity that is much greater than the affinity of this base for that proton, right? So the conjugate base wins out this battle, this competition between the strength of these two bases, and then the equilibrium ends up being displaced to the left and having a quite low K sub A value. Okay, so in this view we have seen generalities of acids and bases, and then we have discussed acid strength using at least 3 parameters. First, we can talk about the position of the equilibrium. Right? For strong acids, the equilibrium is very displaced to the right. For weak acids, the equilibrium is displaced to the left. Okay? We can also quantify the differences between strong and weak acids using the value of the equilibrium constant K sub A. When K sub A is larger than 1, then we'll have a strong acid. If K sub A is lower than 1, and generally is much lower than 1, then there will be a weak acid. And finally, we can also establish the comparison between weak acids and strong acids by looking at the strength of the conjugate bases. And when the conjugate base is very strong, then the acid is weak, and strong acids generate very weak conjugate bases.